This is problem number 17 from section 3.5. Here we're dealing with a zero eigenvalue. We're given our matrix. We use our characteristic polynomial. We find two distinct real eigenvalues. However, one of them is a zero. Even with zero, we can still find a corresponding eigenvector. We use our standard equation that says A times the eigenvector that we're looking for is going to be 0 times that eigenvector. And we do find a non-trivial solution. We find this first equation says that 2y must be 0. The second equation says that minus y, or y, must be 0. Any vector of the form where the y value is 0 will be an eigenvector in this case. And in the second situation, lambda 2 is equal to minus 1. Same thing. We set up our system of two equations, two unknowns. We get two redundant statements. The first one says x has to be equal to minus 2y. The second one says y has to equal y, so no restriction whatsoever. They're not redundant, but no restriction whatsoever. Any x and any y will satisfy this equation. So we use the first one that says x has to be negative 2 times y. So if y is a negative 1, then x is a positive 2, and that's a perfectly good eigenvector. In part C, it says to sketch the phase portrait, and it's important here to recognize and include our two known eigenvectors. So here's v1 corresponding to lambda is equal to 0, and minus 2 minus 1 would look something like this. So this corresponds to the direction of v2. Sorry, it's poorly drawn. Okay. When we look at our general solution, I'm going to jump ahead to part E and then come back and finish the phase portrait. We see that we do our standard thing. We have a k1 e to the lambda 1 v1 plus k2 e to the lambda 2 v2. However, in this case, because lambda, and there's a t here, I'm sorry, t here, because lambda 1 is 0, this term is rewritten as just k1 times v1, and our v1 in this case is 1, 0. And k2, our lambda 2 is negative 1, so negative t, and our eigenvector is 2 minus 1. What's important to note is that in the situations where k2 would be 0, k1 is a non-zero constant that places us anywhere along the x-axis. If k1 is a 1, it puts us here. If k1 is a 2, it puts us here. 3, 4. So we can move all along this axis. This expression is independent of time. These are equilibrium solutions. And so, as you'll see, the book will draw, and I'm drawing now, big fat dots that represent equilibrium solutions, meaning that if you start at one of these points on the x-axis, you never leave it. The system will not take you away from it. So the entire x-axis is a infinite list of equilibrium values. But if you start with an initial condition somewhere off, suppose you start up here, that's your initial condition. What is your fate? Well, I also forgot to include that since lambda 2 is negative, that means that anywhere on this v2 direction, we are moving towards the origin. So a solution that were to start somewhere on this, anywhere on this line, will move towards the origin, and you can see that that's true. The statement says that we are simply moving the direction 2 minus 1, but as time evolves, this term is getting smaller, and if k2 was a 1 and the k1 was a 0, we would be on this line moving forward. What if we're not on that line directly? We will always be moving in a direction parallel to the v2 direction. Missing my mark. So if I was trying to go through this point, I'd be moving in the v2 direction moving towards one of these equilibrium points, and I'll make it a little clearer in a second. But so if I were to start on this side, I'm moving parallel to v2 until I bump into one of my equilibrium points along the x-axis, and my motion, if I were to have started here, I'd be moving in this direction, and so you're getting a rough idea of what our phase diagram will look like. A series of lines parallel to v2, moving up and stopping at the x-axis. Okay, that's our phase portrait. Finishing this up quickly, here's our phase portrait. In D, they say, well, suppose you're at the location 1, 0. Suppose you're at the location 1, 0, somewhere, let's say around here. Well, that is on our line, our x-axis, and so that is an equilibrium value. They say, sketch what the solutions would look like. Well, if I'm at 1, 0, and I'm an equilibrium point, then my x of t graph will stay at the value 1, and the y of t graph will stay at the value 0 because it's equilibrium. It doesn't change. Finally, then they ask, but I've already written it, for our general solution in part E and part F, find the particular solution that goes through 1, 0. Well, again, I could take my general equation and say I'm looking for a solution which at time 0 is 1, 0, and that leads me to a k1 times 1, 0 plus a k2 times 2 minus 1. And it's, I think, clear that we'd end up with k1 equals 1, k2 equals 0, and so our solution is simply 1, 0. Very quickly, I just want to give an example of what it would look like if we were starting at a different, somewhere off of the x-axis. So suppose we were to start at the point 3, 4. Again, here's our general solution. I would plug in 3, 4 at time 0. I would get k1 times 1, 0 and a k2 times a 2 minus 1. Two equations, two unknowns. I find that k2 is a negative 4 and k1 is 11. So here's what a particular solution would look like that passes through this initial point right here at 3, 4. Based on the phase diagram, and I've shown you again what the V2 vector looks like, the direction of it, we would then conclude that what we're being told here is that as time moves on, we start at time 0 at 3. 8 minus 11 at time 0 is 3. But as time moves on, e to the minus t gets smaller, so 8 times it is less than 8. And we're subtracting less and less from 11 as time moves on, but we're approaching the value. The limit as t goes to infinity of this value is 11. The y value starts at a height of 4 and asymptotically goes to 0. 4 times e to the minus t as t moves forward goes to 0. But the direction that we are moving in is this is a constant, this is the direction of movement, and so we would see, starting here at time 0, that we're moving parallel to V2. The point that we're approaching, of course, is the point 11, comma 0. We never reach it. Neither of these terms, this term never reaches 11, and this term never reaches 0. But that's what a solution would look like if we started here. And as time moved backwards, so this is t is equal to 0, and let's say at t is equal to minus 2, I could be up here, and that's roughly what's happening. Okay, good luck.